So this course is on control, or say feedback control, automatic control. So well, if you want to control things, nowadays you need to control a lot of things, right? So you might want to control a robot. Might control like a airplane or rocket or whatever. So this is essential. You want to control things. You want things to move in a desirable way. You need to study control. So actually, this is a textbook we're going to use. It's authored by myself and another professor who is actually a famous professor in Louisiana State University in the U.S. So you see some examples here. See in the cover page. This is a satellite. This is the airplane. You have a boat. You have a like a vehicle. So in order to control those things, you need to have some sort of theory. So that's why we're going to do control theory this semester. And not only theory, we're going to also do experiment. We're going to, to control some real stuff, right? Okay, before we start the technical presentation, so I just want to talk about some logistics. So in this course, we're going to have maybe the first important thing is the grading scheme. So how you're going to finish the course and get the grade in the end. We're going to have a final exam. So this will be 50% of the whole grade. So we're going to have a midterm. This will be 20% of the whole grade. So the midterm will be held on 28th of March. And during this time, during this class time. So we're going to have homework. Maybe about 6 times. So every 2 weeks we're going to have a set of homework problems. So I'll give you probably starting from this week, maybe on Wednesday, I'm going to give you the first set of homework. You will have 2 weeks to work on homework problems. In the end of 2 weeks, you submit your homework, and I'll give you this set. Okay, so that's how it works. So this is what we about 6 times. We're going to also have a lab. Actually, that's the most important for the course. Not in terms of grade, but I really, and I want to stress the importance of this point. We're going to work on some real stuff. What are the real stuff? Well, I can name some of them, and I'll show you some. One is a motor. That's probably simply the system you want to control. You want to control the motor speed. So like you see motors everywhere nowadays. Motor is easy to control, but we're going to do some other fancy stuff. We're going to control magnetic suspension or magnetic levitation system. So you will be able to control a metal a metal piece, a ball actually, in a magnetic field. So the ball floats in the air. That's one thing I want to control. Another thing I want to control is this so-called inverted pendulum. So inverted pendulum, you see pendulum before. The inverted pendulum goes like this. You want to balance it. Huh? But you cannot balance it, you cannot hold it, directly. You can only move the base so that this thing balances. Right, so we're going to control several stuff like that. Some of you probably want, what is the lab schedule? The lab schedule will be fixed after I get all the enrollment in this course. So the lab time will be fixed according to your need, basically. We'll make sure that all of you will have, will be able to do the lab during your available time. So this will be 15%. We'll have 4 times, 4 labs. So roughly every 3 weeks you will run the lab. So each lab is about 3 hours. So in average, you work 1 hour per week in the lab, but you don't really work every week. You work once every 3 weeks. Okay. So in the lab, probably I'll talk about more about the lab. You'll have to do pre-lab. You need to show up in the lab session. You need to write a report. Those details we'll worry about it later. So the lab scheduling actually is a big issue. So we're going to do it probably after Chinese New Year, and so that we'll make sure that every of you have a good schedule. So, any questions so far? Okay. If you have questions later on, you can also ask me. Textbook is this one. This book is out of print. You won't be able to buy it. We're going to give you basically a PDF version of this book in the Canvas system. We're working on the second version of this, second edition of this book. We haven't finished yet, so that's why we are not able to give this book to the publisher to have it printed. We're not going to cover the whole book. We're going to cover the first 4 to 5 chapters, depending on how far, how fast we go. And so some of you might wonder, what is the syllabus of this course? You can just look at the table of contents of this book, which will be available in the Canvas system. Okay, what else I want to say? Well, now, people talking about outcome-based education. They always ask me to give the so-called desired outcome of this course. Actually, it's kind of hard for me to give a specific outcome. This outcome-based education is new to me, and I don't really know what is the outcome. So let's just skip it. Yeah. What else? Okay, so probably we just go directly to an introduction. Okay. I don't think this is right. I should download. Tell me where can I find a download. Huh? The bottom. Down the bottom. Yeah?
Can you open Chrome again?
Open this
No, Chrome, the browser.
browser. Good browser. Okay. Yeah. Okay, that's good. Browser. Yeah, it's here. Yeah, yeah. That's right. No, it opens in the browser. It doesn't look right. Is it in the downloads?
Yeah, download.
That's it. Okay, introduction. So, what is the purpose of control? You know, what are the main tasks of doing control? I think there are two. One is stabilization. The other one is regulation. So what they are mean by stabilization and regulation, I'm going to talk about those. Stabilization. You know, if you look at this word, it means that you need to stabilize something which might be unstable initially, you know, which might go in an undesirable way. Then you need to control it so that make it work in a proper way. Let's look at an example. Suppose you drive a car along a straight road. All right, so you are the driver sitting there. Of course, the main purpose is to keep the car in the desirable position of the road. You don't want to go off the road. Clearly, without the driver, this car is going to go crazy. It's going to go. Very likely, it's going to go like to the side of the road. So this phenomenon is called instability. We'll say the system without controller is unstable. With the driver, so the driver now is a controller. With the driver, then you can, you know, possibly make it stable, basically. Keep the car roughly in the center of the road. Right? Intuition tells us this is possible. Okay, so this is actually a very simple control system. The car is the thing we want to control. The driver is the controller. So of course, in this control system, it's not a really automatic control. It's a manual control. It's a human control. So it's not an autonomous system. But later on, you can worry about how to replace the human driver by a computer. So then you will have an autonomous vehicle, right? Some terminology. You know, the object which we need to control is called a plant. The plant. Yeah. So this is the car. The controller is the driver. So those are the very basic terms we use in control. So you probably have heard about open loop control, closed loop control, or feedback control, all those concepts. What do you mean by open loop control? Assume that this driver is so small that he doesn't really need to. He doesn't really need to look at the environment. He doesn't really need to see anything. He just he can drive the car with eyes closed. Right? Basically, he can compute what he needs to do in advance. Right? If that's the case, we say it's open loop control. There's no feedback. You don't need to do observation. Well, it's easy to imagine that this is, it's not going to do a good job. You won't be able to precisely compute everything at once. Especially you have uncertainty. You don't know what the wind direction that day. You cannot predict actual road condition. So open loop control is something used occasionally by people in industry, but it's I don't suggest it. So it's basically impossible to do anything good. So later on, when we talk about control, we always mean closed loop control. Yeah, in closed loop control, this driver has to see, just see what is the real position of your car and make adjustment according to your observation. Right? So you basically look at the outcome, and then you decide your control action using your observed outcome. So this is the information actually goes around the loop. Right? So then so for the feedback control. Well, feedback control makes sense. Right? We should be able to control the system. We should be able to control this system. We should be able to stabilize it. Okay, more abstraction. So we have plants. That's a car. We often use a block diagram to depict the control system. So in the control system, no matter how complicated, you have those blocks. You have those arrows, these signals, to connect those blocks. So a plant, in the previous example, is the car. You see, in order to be able to control the plant, we need to have some sort of input. This input is the way to influence the behavior of the plant. If you cannot influence the behavior, of course, you cannot control it, right? So if you want to control the position of the car in the road, you need to have a wheel. So the wheel, that the wheel position that's input. Yeah, so that's then you have kind of the desired, that some kind of concerned behavior, right? This concerned behavior must be described by some kind of a variable, right? So that concerned behavior is called output. So in the previous example, the output is the deviation of the car from the center of the road. the deviation. You want the deviation to be 0, basically. But of course, you cannot keep it exactly 0. You just want the deviation to be small, around the center line, roughly. So that's our output. In addition to the input-output, you may have some other, some other arrows going in, and some other arrows going out. So this arrow is called the arrow means a signal. Okay, so this arrow means a disturbance. The road condition, uncertain road condition, that's a disturbance. Wind condition, the weather condition might be another disturbance, right? All this unexpected stuff. Disturbance is something you cannot do anything about. It's external. From external. You don't know when it happens. When it happens, you cannot stop it. Measurement, that's a thing going out. When you want to control some variable, so this is your concerned variable. Very often you say, okay, in order to control it, we need to observe that variable. We need to measure that variable. So that's why we need to know the information. Right? We do feedback control. We need to know the information about this variable. But sometimes we cannot directly get it. We can only measure some kind of other variable, which might be different from that one. But you can get information about that one from this one. So then we call this a measurement. Measurement is that it's a variable which can be sensed, which can be measured. You can build a sensor, sensor to measure. We often hear sensors, like a temperature sensor. In this room, we have temperature sensors, and we have speed sensors, velocity sensors. All those sensors, we can measure variables in the system. If we know we build a lot of sensors, then we get a lot of information about the system. Of course, we turns out that we should be able to control this system better. Okay. Now we have the plan here. Now. How do we connect the controller with the plant so to get a control system? This is a control system. You see, this feedback control system is a loop. You have a loop here. It goes like this. You have a plant here. You have a controller here. But the connection of controller and plant is through a signal going through this actuator, and also through this sensor. We call this like an input part. So this is the output part, or sense, and the feedback part. The controller needs to have some kind of actuator to manipulate the plant, to influence plant. So a typical actuator is a motor. Nowadays you have all kinds of motors. You have all kinds of you have a linear motor, rotational motor, all of these things. Why we have motors? Because usually the controller processes electric signals. Like a computer, you have digital signals. You go through digital to analog conversion, then you get the analog signal. But this is an electric signal. But the plant, actually, you can have all kind of plants. But probably the most common plants are mechanical systems. like airplanes, like cars, like robots. You have something moving, you know. So how to influence the mechanical system? Usually, you know, you have to have a motor. So this motor convert an electric signal to like a kind of torque, kind of a force to drive the mechanical system. So that's why you have you need to have actuator. Also, a sensor here. What is the function of sensor? You know, you take this measured signal here, but this signal might be, again, a mechanical signal, like a speed, position, or sometimes you have the temperature or pressure or whatever. Alright? Then you need to convert it to an electric signal so that the controller is usually like electrical way. Nowadays it's a biocomputer. So you need a sensor. You build all these things. Actually, you don't really actually build them. So usually this plant is built by something else, someone else. You don't build the plant. What do we do in control? We need to select those things, actuator and sensor. We need to design this. So our focus on the designing. Especially when we talk about the theory on control, our focus is here. Because how to select actuator and sensor is not a theoretical, it's not theory based. You just look at technology and look at what are available in the market, and then you buy them and put them there. But the theory, our theory, control theory, has a focus on the controller. You need to design this controller properly. Actually, you know, if you look at the control system as a you know, like a human body's control system. Controller is our brain, actually. We process signals and make decisions. So plant, you know, you can consider that just arms and our body, you know, we make that way. We need to move in the right way. Sensor, we have a different sensory system, right? Like we can hear, we can see, we can smell, and all these things. Actuator, actually probably our muscles, you can consider as actuators. Also, our muscles here get like an instruction from our brain, right? Then we try to drive this the whole body to move in the right way. So, okay, stabilization. So that's a schematic diagram of stabilization. Put in a more formal way, you know, what is a stabilization problem? This is not really the final mathematical problem. This is just like a more formal statement of a stabilization problem. The car example is just an example. So in general, we give a plant. Right? We need to select a sensor and actuator, and design the controller so that the closed loop system, the whole system works properly, has a good stability. Of course, what do you mean by good stability? You know, intuitively, it's just like it works in a smooth way, roughly, you know, in a desirable way. Okay. All these things will be further formalized using mathematical language later on. And we're going to solve this problem. First, in a mathematical way, then you probably go into a real system and try to apply to real system. Stabilization is the first problem. Now, the second problem, regulation. Now again, we take this car driving as an example. But now suppose that we're driving in a hilly road, up and down, and we need to follow the speed kind of limit. We cannot drive too fast, we cannot drive too slowly, right? So we have a desirable speed. Suppose that the speed is a kind of constant, say 100 kilometers per hour. The road is like up and down. So, what do we need to do? Again, this car is a plan. The human driver is the controller. The speed instruction is external instruction. We have external command. So the external command say, okay, at this segment you drive 100 kilometers per hour. At that segment they drive like 80 kilometers per hour. So that actually this command can change with time. Typically it changes like a piecewise constant way. Huh? Then you say, okay, I drive the car. I wish to keep my speed. Alright, but you have a wind gust. You have like a hilly road up and down, or these kind of things. How do you do it? In a good way. So you first of all, you need to actually try to keep the speed. Actually, you also need to reject the disturbance. Yeah, the wind gust is possible disturbance. And this hilly road is also considered as a disturbance. So you want to reduce the effect of this disturbance. You want to keep your speed as a constant. So how to do it? That's what we worry about in this situation, in the situation of regulation. Again, you can feel open loop control is not going to work well. Right? So you cannot set your pedal position or movement in advance. Right? So you have to make adjustment according to the actual speed. You probably have to somehow compare your actual speed with desirable speed, and look at the speed error, using that error to make adjustment. So again, you see the advantage of closed loop control over the open loop control. So in this case, actually, you may say, okay, what's the difference between regulation and the stabilization? And the main difference is that now we have external command. So control system in all of our applications is supposed to follow an external command. This command again is something you cannot control. Right? So that's why in regulation you have this external command. In the stabilization issue problem, you don't have this external command. So that's a big difference. Now let's look at the block diagram of a regulation control system. Again, you have plant. You have actuator and sensor. You have a controller. But now, see, the difference is that now we have an external command. So external command is called a reference signal. We call it reference signal. The controller takes both the reference signal and the actual, the measurement. Yeah? So basically the outcome of the plan. And make some kind of comparison. So there's two pieces of information. So this R is one piece of information control receives. And R in general changes with time. Y, okay, the measured signal, feedback signal, is a second piece of information, and put it in, and generate control signal. So probably that's the only difference here. See? Only difference you compare regulation and stabilization. So this difference actually is kind of crucial. So this difference makes the controller like more complicated because the controller has to take two pieces of information and send out one control signal. Right? So you have two pieces of information here. This controller, if you look at the information flow, you know, the information flow goes from here to there, also goes from here to there. So you have two parts here. This controller is called a 2 degree of freedom controller because you have one part, you have two parts of the process. So later on, you probably can appreciate this word 2 degree of freedom controller. 2DOF controller. You will appreciate this word further. So regulation problem, if we state it in a formal way, again look at this block diagram. Given a plant, select a sensor and an actuator, and design a controller. So that the output of the closed loop system track the reference signal. So the output Z tracks this R and eliminate the effect of disturbances. Eliminate the effect of the field. So tracking is probably the more important thing. So we're going to look at this tracking feature. You have something coming, and this guy has to follow this guy. So that's an additional feature in regulation problem compared to the previous stabilization problem. Okay, so let's again recap what we have talked about so far. We have two problems, stabilization and regulation. We're going to study both problems and look at solutions. We're going to do experiment on those problems. We're going to have experiment on stabilization problem and regulation problem. So in stabilization problem, you don't have a reference signal. You just want to make things work in a kind of natural way, nice way. Regulation problem, you want to make the system to follow some kind of external commands. Yeah. So sometimes you also have different features in the disturbances, right? So we can look at that later. So the most important difference in the controller due to the presence of a reference signal is that in the first problem, sterilization problem, the controller only takes the feedback signal. In the regulation problem, the controller takes both signals, reference signal and the feedback signal. So that's why this controller is called 2 degree of freedom controller. In order to solve a regulation problem, you need to first solve stabilization problem. So regulation problem can be considered as a further step of stabilization problem without stabilization, you cannot do regulation well. You can see at least, in the regulation problem, you set the reference signal to be 0, right? Or the command is 0, then that's essentially a stabilization problem. So that means even without the reference signal, the regulation system has to work well. So that's why you need stabilization. I think you can have a rough feeling of those things. Okay. Yeah, we have a look at 2 examples, 2 real-life examples, to capture some kind of essential ideas and control. So let's now look at some very basic concepts we need to deal with, we need to actually use in study control. Before we talk about the control system, or even a system, we need to know what is a signal. A signal is a time function. So from real line, z-axis. This real axis is time to a real value. So real value, that's a signal. So very often you can draw a signal by like a waveform. Right? So that's what we often do. So this is the time axis. So we have, say origin is here, that's time equal to 0. The vertical axis is whatever signal. Let's call it xt. So the signal is just like a waveform. It's a waveform or is a time function? That's a signal. Most of the time in this course, we're going to deal with unilateral or one-sided signal. That means that we assume that signal takes value 0 before time 0. Everything's dead. It's silent before time 0. So only the signal start to become non-zero after time 0. Right? Signal, right, is 0 for all t less than 0. And that's called a unilateral one-sided signal. A typical such signal is called a unit step signal. This is something we're going to use all the time. Unit step signal is just like a 0 everywhere here, then jump to 1 after time 0. Okay. You probably have seen this before. So this is probably the simplest signal we're going to use. That we're going to use all the time. Simplest unilateral signal. Unit step, we are going to use a unit impulse signal as well. But this signal is a bit more like a mathematical abstraction because it's a kind of a strange thing. it's not quite a function. It's called a singular function. So this unit impulse signal is defined in such a way. Okay. First of all, it's a zero everywhere, except at time 0. But at time 0, something strange happens. If you integrate from minus infinity to t, well, if this t is less than 0, you see what happens. Because this signal is well, maybe we'll just look at it here, okay? Forget about this step. We are just have a signal 0 everywhere here, 0 everywhere there. It just have something strange happen here at time 0. So if you integrate the function from minus infinity to t, and if this t is somewhere here, it's less than 0, of course, from minus infinity to t, everywhere is 0, integrate is still 0. Okay? But if the t is somewhere here, you know that this is something strange happened at this origin, then the integral from minus infinity to somewhere here becomes non-zero. It turns out that actually the integral is equal to 1 if you integrate from here. So that means, okay, this integral, the integral of the unit impulse function from minus infinity to t is equal to this guy. Right? So you know that the function value is 0 here, 0 over there. So if you integrate from minus infinity to somewhere here, you're doing nothing most of the time, except when you go from here to there, right? Basically, from minus infinity all the way integrate, up to this point, you're not doing anything. And after this time 0, you go further, you're not doing anything. The only strange thing happening is that is from here to there. So this integration actually is equal to the integration from t minus to t plus. No. From 0 minus to 0 plus. Right? That's something. What is 0 minus 0 plus? 0 minus is just a bit before 0. 0 plus is just a bit after. You see that when you integrate, you can simply take that as small integration. You integrate in a small integration. The unit step, the unit impulse, after integration you get a step, unit step. So the integral of this is equal, integral of theta is equal to sigma, then the derivative of sigma gives you theta. This is according to the calculus. The differentiation is the opposite. It's the inverse operation of integration. So now you see that this definition of unity impulse signal is kind of abstract, right? It defined not as a usual function we define as the value at each time. To define in terms of this differentiation or integration. But we can actually we can also use some kind of approximate argument. Suppose that we have a signal like this. So this can be considered as an approximate step. Instead of having a jump at the time 0, now I have like a slope, a ramp, going like a very rapidly to 1. It takes a time, an epsilon time interval, go from 0 to 1. So certainly, this is approximation of this. Now let's take the derivative of this. The derivative of this, see, we go 0 here, and 0 over there, the derivative. But this derivative is 1 over epsilon, very high. So when you shrink this epsilon, make this epsilon very, very small, then this interval becomes very, very small, but the height becomes huge. The area below this is a constant, is 1. So this is an approximation of data, the impulse function. Okay. When epsilon becomes smaller, you get a better approximation. So that's a whole idea here. Yeah, you can always think this data function in this way. So it's a very high impulse, a very narrow impulse, so that you have a fixed area. Those two signals are the ones we're going to use all the time. I think in other courses we also use these two signals. So you can imagine also other unilateral signals. So you see that this sigma t is not only itself is not only it's not only can be defined by like independently as a signal, but it can also be used to describe or to write a unilateral signal with other features. For example, we say sine function, sinusoidal signal. That's something you very often you see. But sinusoidal signal, right, goes from minus infinity to infinity. It's just a periodic going up and down. You multiply a data, what do you get? You get a unilateral sinusoidal signal. Basically, it's a sinusoidal signal starting at time 0. So before time 0, it's just flat, 0. Okay? So this sigma t gives you a convenient way to describe a unilateral sinusoidal signal. Also, this signal, this e to the lambda t, e to lambda t is exponential signal. This kind of signal is often kind of some kind of a common signal. Exponential signal, probably we should look at it more closely. suppose we wish to look at the unilateral exponential signal. So in that case, we know that it's, this side is always 0. So we only need to worry about the positive the positive time axis. Positive time axis, okay. When this t is 0, when this t is 0, e to the power of 0 is 1. It starts from here. 1. So when time goes by, how is this going to go down or go up? Huh? Yeah, it depends on lambda, right? So if lambda is less than 0, it goes down, right? So it goes down exponentially, we say. Exponentially goes down. So in that case, this lambda is less than. When t goes to infinity, converge to 0. Right? It will never be 0 exactly. It converges to 0. And monotonically converge to 0. Right? That's a So when lambda is greater than 0, it goes up. Yeah, it shoots up. Yeah. It shoots up like that. Okay? This is bad. Actually, we don't like to see this. We wish to see things, converge and smooth, and it doesn't explode. So if you see something like that, this is a typical unstable behavior. Also, if lambda is equal to 0, then it's just like it's a constant. This is yeah, it's an exponential function. You will see this very often. Right. Exponential function. So we have some rough idea about signals. Let's now look at a system. System processes signals. So we often use a block like this to denote a system. And then you have those are signals, those arrows are signals, those lines, these arrows are signals. Then these are we call this input signals, the output signals. In general, a system might take many input signals. So if you write it in this way, you see that you have a U1, UM. Those are all signals going in. You also have output signals going out. You have M of those input signals. You have P output signals. Right? So if indeed this M is greater than 1, P is also greater than 1, then you say, well, this system has multi-input, multi-output. Then it's a MIMO system. So in the case of MIMO system, you put all the inputs in a vector. In the vector, you use like a UT. So this U is different from this U. This is a bold U. So you see it's darker, thicker. So we use a darker and thicker symbol to denote a vector. So vector signal. Similarly for y, you have a darker y. So this is a dulled y. And the signal basically, with the input-output relation of a system, we write this way. So you take a signal and put it in the system, and then the system is going to generate an output. Right? So basically, you take a signal, basically a time function, it's a whole function, okay? You send it to a like a processor. This system can be considered as a processor. It's like a black box. You don't really know what's going on inside. Right? You send it in, and in the other end you have something coming out. So that's the thing coming out, of course, is called the output. Notice that this system takes a whole signal as input, more than just a value. You know, it doesn't take just 5, but it takes a sinusoidal signal into the system and generate now probably an exponential signal. It doesn't generate like a 10 or a number. Okay, that's something you have to keep in mind. It's different. The system is different from a function. Function is that you give a number, then the function generator is going to give another number out. You know, that's a function. So the system is actually more complicated. It takes time function and it gives out another time function. Okay. We have to talk about. We have to, count the number of inputs and outputs in the system. If indeed the number of input is 1, the number of output is also 1, in that case we say the system is single input, single output system, SISO system. Actually, the main focus of this course is in SISO system. So this is the first course in control, so it's an actual introduction. Introduction to control stuff. So we look at a simple case first. Of course, you can have a more complicated case. In general, you have a MIMO system. MIMO system nowadays, of course, most of the system. Later on, I mean, in the future, maybe it happens that you're working Boeing, you're working Boston Dynamics. All these companies, those are robotics or whatever. They have a MIMO system. So the control of MIMO system, of course, requires more knowledge, more like experience. So later on, you're going to worry about that. If you go to graduate school, right, to study the control of those things, then you'll learn more about MIMO system control. So this course, I'm going to start from the basics. SISO systems. Occasionally, like this, this something in the middle. With only one output or one input, and you get sometimes system which is a bit more complicated than that, but less general than this. Well, occasionally we deal with that kind of systems, but again, it's not much harder than the single system. Therefore, all kinds of systems. Let's again look at some very simple, typical ones, and get some kind of feeling how to classify systems in different ways. Previously, we classified systems according to SISO, MIMO, and things like that, right? That's one way to classify. There's also some other ways to classify. The simplest system is called a static system. System without memory. So in this case, well, if we have a U in certain waveform, the output is, well, the output has the same waveform. It's just like a scale it, amplify it, or scale down a bit by a constant. So this system is called a proportional system. Proportional system. Simply called P system. Memoryless, static. That's too simple. Actually, this is just like an amplifier. You know, whatever you have, whatever input signal I take, I just multiply a constant and send it out. Too simple. Not we need to use it, but it's not exciting. Dynamic systems. Well, dynamic systems, then that makes the whole theory interesting, and of course, non-trivial systems are all dynamic systems. The simplest example of dynamic system is an integrator, or simply I system. Integrator is that you take the input and then integrate it from minus infinity to t, and it gives out the integration gives the output. You see, of course, this system has memory. What happens in the past is going to show up. Show up in the interval, and it's going to, give you some kind of different value at any particular time. Possibly you have a gain, you have some kind of a coefficient here in I. So they are according to whether you have memory. Another way is according to whether you have or according to this so-called causality. So what do you mean by causality? A system is said to be causal if the output value at the same time does not depend on the future input. Okay? Basically, it doesn't have some kind of a prediction. You cannot predict the future. So all physical systems are like that. If time goes in one direction, you cannot go back. Right? So you can have the past input affect your current output, but the future input cannot affect the current output. Okay? So that's the concept of causality. This is causal. This is also causal. But this is just simply no memory, of course, it's causal. The current output value depends only on current input. It doesn't depend on the future, doesn't depend on the past. So that's a simple situation. Of course, that's called causal. So this integration, this is an integral system. The output depends on the past input, and of course the current input, but not the future input. And this is causal. The integrator is causal, so this is causal. So if we put this there's a P system and an I system together, add them together, then you get a PI system. non-causal system. Well, something, the output of system at this particular time depends on the future input. That sounds strange, right? Indeed, that's strange. Well, no physics system like that. Although maybe in your signal processing or in your whatever course, you say okay, you can do non-causal, you can design a non-causal system, but that's again is not a real time. It's not a real time non-causal system. It's just like in a different time frame you can talk about. In real time, there's no non-causal system. Then you say, okay, what happened to this system, this so-called derivative system? You probably have heard people talking about PID, etc. Then you know that the P and I are causal. What about D? What is D system? D system is like that. The output is a derivative of the input. The output is derivative input, then it is causal. Or say, in order to take this derivative, you need to know the value of u in the neighborhood of t, right? You know that you fix your t, right? Particular t. In order to get the derivative, how do you get derivative of a function? You need to know what happens here around that particular t, before or after. Especially you need to know after this t, what the value of the input. So this is not causal. It's non-causal system. Derivative non-causal. So then you say, okay, I can buy it. Theoretically speaking, it's non-causal, but the people use it. Then how do you do it? I'll just tell you that the people use a modified version, just PID, whatever. They don't use the exact ideal D. They use a practical D. So not the practical D, not quite in this form, not quite in that form. So I tell you what is a practical D later on. Okay. We also need to look at two very simple but not quite a seesaw system. Like this kind of again some very trivial system. This system has two input, one output, so it's actually MISO. So what it is that the output is U1 plus minus U2. You open it, we call it summing point. This you have actually one input, two output. Both y1 is equal to u and y2 is equal to u. So this is called a pickoff point. Those are essential part of a control system. Although you say, okay, theoretically speaking, the MISO and SIMO, they're not SISO, but it's two. We use it all the time. We don't worry too much about whether it's a SISO or not. Okay. Right, let's now, so probably after we talk about the signals and systems, we can actually make this stabilization problem, regulation problem, a bit more abstract, like more close to like a kind of a theory. stabilization. Given P, this plant. Design C, CC. Again, I want to emphasize that in this course, we look at the single input, the single output, CISO P. CISO P. We design the CISO C, again, the single input, single output. And we just connect this thing together, forming a closed loop system. Right? We want this closed system to have a good stability. Again, good stability, quotation marks, it's again a theoretical concept that later on we're going to worry about. So that's a more abstract version of stabilization. So in this case, you see that the plant, originally you have like a disturbance coming from here. You have a Y, you have a Z and a Y. You have two outputs, which one signals the concerned variable, another is like a magnitude. But here we just want to simplify things. We assume that the Y and Z are the same, basically. And also, there's the disturbance coming from input and output instead of going into inside. We don't want to worry about this multivariable stuff, like two. So we just say, okay, potentially you have an input signal, the input disturbance, output disturbance coming in, and you want this system to work properly. Okay. Feedback system for regulation again, and the plant becomes like this. The disturbance now is split into a disturbance here and a kind of noise there, and the key difference is that now C. Now I use a bold letter C to signal a 2-degree freedom controller, basically. You have two inputs, one output. So this is CISO, say, well, in this course, this is always CISO. CISO system, but even in that case, the controller now is not CISO. It's VSO. Right? We have two input and one output. So this kind of controller, again, 2-degree of freedom controller. Why? Because if this system has a 2 input and 1 output, so in some way you can think this system can be decomposed into 2 systems. One is the system go from here to there. The other one is this system go from here to there. And you have 2 systems. So this system can be written as in this way, 2 systems, C1 and C2. So you have C1 goes this way and C2 goes this way. So again, you see that this system we need to learn how to deal with this kind of system, and this decomposition is one way to deal with it. So again, like in this regulation problem, the reference is here. So reference is a key, and you want this to track this, to follow this. Okay. So I think now I stop here today. Later today or tomorrow you will see more things in the camera system. You probably will see a syllabus, you can see the notes. Please read the notes. Right? The notes is just like a book. Read it.